Up until now, we in the last lecture, we finished talking about nuclear medicine and a couple of imaging modalities called PET and SPECT. So PET was a positron emission tomography, and SPECT was single photon emission tomography. And again, those use radioactive pharmaceuticals, which is a radionucleotide bound to some biological agent, which can target a specific organ or a specific function in the body, and then gives us a way to visualize how the physiology or the metabolism is happening in the body. Okay, very useful for diagnosing things like cancers and different bone diseases and stuff that have different metabolic activity than healthy tissue. Now we're going to be moving on, and now we're going to talk about MRI imaging. We're going to move on now and start. I'm going to introduce today MRI, and which stands for magnetic resonance imaging. Okay, so again, MRI stands for magnetic resonance imaging, and it's an imaging modality that uses the combination of powerful magnetic fields and radio waves to produce images of the body. And we'll talk about how this is done, okay? So if you have, looking at some of the physics, if you have current, okay, traveling in a circle, okay, maybe a current that we'll call I, okay, if you have a current traveling in a closed loop, as you may recall from physics, if you have a closed loop and current traveling in a closed loop, anytime this happens, you're going to get a subsequent magnetic field, okay, or a magnetic moment, okay? This magnetic moment follows the right-hand rule. And the strength of this magnetic moment, mu, will be equal to the current times the area. So I stands for the current, and A is the area of the closed loop that it encompasses. Okay. Now, if we look at, for example, something like a hydrogen atom, which, by the way, you may or may not know this, or you may not realize this, but atoms, right, they spin, okay? And they also have charge. So a hydrogen atom has a positive charge, and it's spinning, okay? Okay. And because you essentially have a charge that's spinning and causing a closed loop, it will also produce a magnetic moment. Okay. In fact, so anytime you have any kind of charge going around in a closed loop, this is going to happen. This happens even with the Earth. Okay. You know, the Earth rotates, the Earth spins, and subsequently it produces a magnetic field that surrounds our Earth. It actually acts as a shield for radiation from the sun. The sun is spinning and it has charge on its surface, and it produces also a very powerful magnetic field. Almost all the planets have a magnetic field, by the way. But also, if you even go down to something as small as our atoms in our body, our hydrogen atoms, any atom that has a charge uh, and spinning will produce its own small magnetic moment. Okay, even if you think about it, if you recall from like chemistry, uh, you may have seen these large chain fatty acids, right? That are made out of carbon, 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 and attached to those carbons are what? Hydrogens, right? So there's hydrogens, hydrogens, hydrogen, hydrogen. So each one of those hydrogen atoms, they all are spinning, okay? They're spinning and they all have a positive charge. And because they have charge and they're spinning in a closed loop, they're all producing a very small magnetic field, okay, or a magnetic moment. So you might ask, well, if our, and by the way, you have tons of hydrogen inside your body. In fact, the body is mostly water, right? And so there's lots of hydrogen in the human body, including in all these different fatty acid chains, and uh, um, this happens all over. Okay, so hydrogen's pretty abundant in the human body, and each one of these little hydrogen atoms are producing its own small magnetic field. And so you might ask, well, if I have small magnetic field in my body, how come we are not magnetic? How come we don't attract metal? And the answer is because all these little magnetic fields are all randomly oriented inside of our body. Okay, some are pointing this way, some are pointing this way, some are pointing this way. Okay, and so they're all spinning randomly. So essentially, there's no overall net magnetic moment. Okay, so they all kind of canceling each other out. Um, but as it turns out, we can use this uh, in uh, in magnetic resonance imaging. Okay, so if we put this in the presence of an external magnetic field, okay, a powerful external magnetic field that I'll call B, okay, and I'll just draw it like this. This will be B. B is a powerful external magnetic field. What will happen to all of these hydrogen atoms with all their little magnetic moments is that they'll align themselves with the external magnetic field. So all these hydrogen atoms will temporarily, while they're in the presence of this external magnetic field, they will align themselves with this external field. Okay. And there's a couple of one of two ways that they can align. They can align in this parallel position, or they can align in this anti-parallel position where it points down. And it'll do whichever one requires less energy. Okay. Um, and so another thing that happens as you put these hydrogen atoms in the presence of a strong external magnetic field and they align, they also do something called precession. Okay, so let's talk about what is precession. Well, if you recall, all of these atoms are spinning, right? Okay, so they're all spinning, so they have some angular momentum. Since this one's upside down, it's spinning the other direction. Okay, and because it's spinning, it causes this hydrogen atom to kind of wobble. It wobbles around the axis of the moment. Okay, so each of them will kind of wobble around. Okay, so this external B field is uh, pulling them all in a certain direction so that they're all aligning with the external B field. But because they're spinning, they don't align completely to that external B field. Instead, they precess about that B field. So let me write down real quick the definition of precession. Okay, so precession happens when a force is applied to spinning to a spinning object with angular momentum. It will subsequently have a directed force at right angle to the external force. Okay, this is what precession is. So let me try to draw it in a little bit different way and see, and hopefully that'll become a little bit more clear for you. So let's say this is my hydrogen atom. Okay, and remember the hydrogen atom is spinning. Okay, so it's spinning. And because the hydrogen atom has a charge on it and it's spinning in a closed loop, it's also producing this magnetic moment. Okay, and when I put this in the presence of a strong external magnetic field, the magnetic moment will align itself to that external magnetic field, but because it's spinning, it won't align perfectly. Instead, it'll wobble around that external magnetic field or precess around it. So let me draw in green the magnetic moment, okay, will wobble around that external B field or precess around it, okay? Um, okay, so this is what's called precession, okay? So it's kind of this wobbling. And let me try to show you guys a little video and see if it will make a little bit more sense. What is precession? Okay, let's see if I can pull up this video. And I suspect most of you have seen this phenomenon of precession before and maybe not have realized it. But if I can get this video to work, it's going to show a video of a spinning top. Okay. Okay, so here's a spinning top. Okay, so it has angular momentum because it's rotating, but there's also an external force called gravity pushing down on it, right? But you see how it's wobbling? It's wobbling about the external gravitational force. That's called precession. See how it wobbles? It doesn't just sit there and spin perfectly. Instead, it wobbles about. Most of you have probably seen this before. Maybe you've even done this on yourself with a spinning top. You see how it wobbles? See how it doesn't spin just perfectly? This is because there's an external gravitational field pushing down on it, and it's spinning. So it has this force being applied to the spinning object with angular momentum. It produces a directed force at right angles, which causes it to wobble. Okay, so this is a good visual here. So imagine your hydrogen atoms are all doing this. The magnetic moment in your hydrogen atoms, when they're placed in the presence of a strong external B field, um, they continue to spin and they precess. They precess about that external B field. Okay, let me just show you one more video of a spinning top. Here you can see the precession uh, pretty easily. See how it kind of wobbles about the external gravitational field. Now remember, the external gravitational field is pointing straight down, right? And so that's going to be an external force applied to a spinning object that has angular momentum, which produces this directed force at right angles, which causes it to wobble. Okay, because this one's a very highly precision top. It doesn't wobble very much. They're trying to minimize precession, which, as a side note, by the way, whenever you're trying to launch a rocket into space, that's an important parameter to try to control. You don't want it to. You don't want your rocket to start precessing too much, because then it'll blow up. Um, so coming back here to our example here. Okay, so again, we have a hydrogen atom. Okay, which has a charge. Okay, which goes in a closed loop, which produces a magnetic moment. And if you put this hydrogen atom in the presence of an external B field, okay, it's an external B field, all of the hydrogen atoms will align with that B field, but because they're spinning, the magnetic moment of those hydrogen atoms will precess about the external B field, okay? And as it turns out, the frequency of precession okay, the frequency of precession is calculated by multiplying the gyromagnetic ratio times the external B field. So this this symbol here is the gyromagnetic ratio, and B is the strength of the external magnetic field. Okay, so the frequency at which it will precess. So remember, frequency is really nothing but cycles per second. So how many times it goes around in a second, right? Can be calculated as the gyromagnetic ratio times the external magnetic field. Okay. Um, and as it turns out, let me draw again down here. Let me draw again down here, a hydrogen atom again, okay? And again, this hydrogen atom is spinning. Has a charge, spinning in a closed loop, therefore producing a magnetic moment in the presence of an external B field. Okay, so this magnetic moment is precessing or wobbling about that external B field at a certain frequency. So this is happening at a specific frequency. And you can calculate that frequency with the gyromagnetic ratio and the B field, the strength of the B field. And as it turns out, if you expose this to, if you inject a radio frequency into this scenario at the same frequency, it'll a phenomenon will take place called resonance. Okay, so if you recall RF, so radio frequencies are some electromagnetic radiation, right? Or it's light. It's light in the radio frequency part of the spectrum, which we can't see. But light is electromagnetic energy, okay? So what does that electromagnetic energy mean? Well, for example, if this is the light, um, light is made up of oscillating and alternating electric and magnetic fields that propagate, okay? And as it turns out, these electric field and magnetic field are perpendicular to each other. So the magnetic field would look something like this, okay? And the, like I said, the electric field and the magnetic field of this electromagnetic radiation, which is light, which is a radio frequency, propagates through space like this, which we don't fully understand. You know, how does light travel through space? You know, every other kind of energy that we're familiar with requires some kind of medium to travel through. Like sound waves require a medium like air or some other medium to travel through. The sound waves won't go through space, a vacuum of space, okay? But light can somehow propagate itself through space. And they think it's got something to do with the bootstrapping of these alternating external alternating electric fields and magnetic fields, and somehow it propagates itself along. Um, but in any case, even though we don't fully understand that, we do know that light, or RF, is made up of electromagnetic fields, electromagnetic radiation, which have an electric field oscillating with a magnetic field. Okay, and it does this at a certain frequency. Okay, so there's a whole bunch of different radio frequencies. Okay, and as it turns out, if the frequency of this light, okay, so if the frequency of the light is at the frequency of precession, if the frequency of light, or the RF, matches the frequency of precession, okay, what will happen is called resonance. You get resonance. It will resonate. So, what does it mean to resonate? What is resonance? Well, you might have heard like somebody sharing a story, and somebody says, "I really resonate with that." That means like I get that. Um, but in science, what it means is if two things are happening at kind of the same frequency or same energy level, you'll get some constructive interference pattern, where they will absorb one energy into each other and become stronger. Okay, so this is what resonance is. And so when this happens, when the frequency of the RF electromagnetic pulse, okay, so this is a pulse, is injected into this system where you have a hydrogen atom in the presence of an external B field that's precessing about that external B field. If the frequency of precession matches the frequency of the RF electromagnetic pulse, they will resonate, and and the what will happen is the hydrogen atom will absorb the energy of the hydrogen atom will absorb the energy of the RF pulse. And so let me show you what it looks like when that happens. So again, you have your hydrogen atom, which is spinning. Okay, in the presence of a external B field. Okay, and it's producing its magnetic moment that's precessing about the external B field. Well, what happens when this RF pulse matches the exact frequency of precession? The frequency of the RF pulse matches the exact frequency of precession. It'll resonate and it'll absorb that energy, and it'll actually tilt the magnetic moment. Okay, it'll tilt the magnetic moment on its side like this, and cause it to precess about like this. Okay, So when that RF pulse comes in, the magnetic moment, because it absorbs energy, it gets tilted on its axis like this, okay? And then when we turn off that RF pulse, the energy that the magnetic moment, the hydrogen atom temporarily absorbed, it'll release it and go back up to its original angle of precession. And as it does that, it'll give off a radio wave, an RF frequency. So in, let's see. So in this, when it tips it down, this is when it's resonating. Okay, that's where it resonates. And this is when you turn off the RF pulse, it releases that energy. I believe the gyromagnetic ratio is the ratio of the magnetic field to, I can't remember the other, to the angular momentum. It's the ratio of the magnetic moment to the angular momentum. And so different atoms will have different gyromagnetic ratios, but hydrogen atoms will all have the same gyromagnetic ratio because their angular momentum should be about the same, and their spin is all about the same. And so the gyromagnetic ratio for hydrogen is kind of fixed, okay? And what can change is the strength of the external magnetic field, because remember, we are applying that external magnetic field. In fact, let me show you. If I drew a graph, okay, of let's say, let me draw down here. Let's say I have a tube, okay, in an MRI machine, okay, and then I've put a patient inside the tube. Okay, and we look at the strength of the B field along the z-axis, okay? The strength of the B field is actually not constant throughout the length of that tube. It's actually linearly increased, okay? So the strength of the B field changes, okay? And let me tell you why we do this. We do this so that we can have different frequencies of precession, okay? Because the frequency of precession is equal to the gyromagnetic ratio, which is constant because it's all hydrogen that's spinning and producing that magnetic moment. But the only thing that's changing is the B field, okay? So along this, let's say at this point here, let's say at this point here, the B field strength might be B naught, okay? And then over here, at this point here, the strength might be B1, okay? So the hydrogen atoms in this section of the body will be precessing at a different frequency than the hydrogen atoms at, say, at this part of the body, okay? So as it turns out, this is how we select, or this is how we do slice selection in an MRI, okay? Because we know the strength of the magnetic field because we're applying that, okay, and if we know that if we inject an RF pulse in here at the frequency of precession, we can get these hydrogen atoms to resonate. We can get just one slice of the body to resonate, and we can image a slice. So let me show you how that's done. And let me tell you real quick this important parameter called the Lamar frequency. So the Lamar frequency is this frequency where they will resonate, where the RF pulse matches the frequency of precession, okay? So if you wanted to image this person's belly, for example, or their torso, all you'd have to do is inject an external RF wave, okay, an RF frequency equal to the Lamar frequency, which would be the gyromagnetic ratio times, in this case, V1. Okay, so you have to inject an RF wave with a frequency called the Lamar frequency that matches the frequency of precession of the hydrogen atoms in this slice, which is, let's say, the patient's torso. And what will happen here is all of these hydrogen atoms, because the resonant frequency, because of the RF frequency matches the frequency of precession, they will resonate and it'll absorb that energy. And all of the hydrogen atoms will get tipped on their axis because they absorb that energy. Okay. And then if we turn off the RF pulse, these hydrogen atoms, just like I drew up here, okay, right up here, when we turn off the RF pulse, this resonates with RF pulse. And this is when it gives off RF when the pulse is turned off. Okay? So again, when it resonates, it absorbs that energy. And then you turn off the pulse, and it wants to spring back to aligning with the external magnetic field and precess about it. When it does that, it has to release the energy that it gained when it was resonating. And when it does that, it will release an RF signature, okay, which is picked up by an antenna. And as it turns out, different parts of the body, different tissues, okay, depending on how they're bound, you know, hydrogen might be bound to water, for example. Hydrogen might be bound to a carbon in a long fatty acid chain, okay? Those will release that energy at different rates, different times. So that gives rise to contrast and allows us to image the human body using this magnetic resonance imaging, okay? It's these, the time it takes when we turn off that RF pulse for it to then release that RF energy and give that pulse back will change based on the tissue that the hydrogen atom is attached to. Say, for example, attached to water, it'll release it a lot faster. If it's attached to a fatty acid, it won't release it as fast. Okay. And so different tissue will have different these releasing rates, and we call these releasing rates time to echo. Okay, um, and so this is how MRI is done. So this was just an introduction. Hopefully, you may or may not completely understand, but we're going to continue on this in the next class, and it'll hopefully start to become more clearer on how this is done. But these are some of the basic principles of MRI. Again, it uses combinations of magnetic fields and radio waves to produce images. One of the big benefits here is it doesn't use any ionizing radiation like in X-ray and nuclear medicine. Nuclear medicine, we were using, in a PET scan, you're using a positron that emits 511 kilo electron volts. Remember, it emits back-to-back photons, so that's 1,000 kilo electron volts. Tremendous amount of energy. Gamma rays. In X-rays, again, you're working with ionizing radiation, which can damage the body. In this case, you're only working with magnetic fields, which, to our knowledge up till now, don't hurt the body. Okay, just momentarily rearranges the magnetic moment of our hydrogen atoms. Okay, and RF is part of the electromagnetic spectrum that has pretty low energy, or it's safer energy. We got radio signals all around us. We got our cell phones, we got TV signal, whatever, are usually just RF, okay? And so RF energy is non-ionizing radiation. So MRI, as it turns out, is very, very safe. In fact, we don't know about any negative health consequences due to it at this time. Does the RF only target the hydrogen atoms? Well, it's not necessarily just the hydrogen atoms. It's the frequency of the RF is matching the frequency of precession of the hydrogen atoms. And it's purposefully done based on the gyromagnetic ratio of hydrogen and the strength of the B field at that precise slice of the human body, or that location. Okay, so, and as it turns out, in the next lecture, we will talk, there's only a few amount of atoms that will produce a magnetic moment. Okay, so hydrogen is one of them, and it's the most abundant in our body. Okay, so not all atoms have a charge on the surface. Some of them have they cancel each other out, so they don't have any net charge. Okay, so they won't produce a magnetic moment. So very few atoms do. Something like phosphor, I believe, will. Carbon-13 will, but as it turns out, we don't have carbon-13 in our body. We have mostly carbon-12. But hydrogen does have a charge on its surface. It's a charged molecule, and it spins, so it produces a magnetic moment. So as it turns out, we don't have as much phosphor in us, and we don't have as much carbon-13 in us, but we do have a ton of hydrogen, because our bodies are mostly water. Okay, so the RF, the frequency of the RF is really targeting the frequency of precession of these hydrogen atoms. And again, it can be done with other atoms like phosphor-31 or something like that, which I'll show you in the next class. But by far, MRI is sometimes called hydrogen imaging. Okay, by far we're imaging the hydrogen in the body, which works out well because the body's made up of a lot of water, and it has a lot of hydrogen atoms in it. The gray matter, white matter of the brain, the cerebral spinal fluid, all have different time to echoes. And I'll introduce this parameter in the next class. This time to echo is how long it takes for the hydrogen to snap back. Once that RF pulse is turned off, the external RF pulse is turned off, and that energy is absorbed by the hydrogen atoms. And when we turn it off, it wants to release it back. And the time it takes to release it back is something called time to echo. You know what? I may have got that wrong, but they call it a T1 and a T2 parameter. There's two parameters because they're spinning and they're trying to realign themselves to the external magnetic field. And when they realign themselves, they let go of this RF energy. Two parameters come from that. One of them is called T1, and the other one is called T2. One of them is time to echo. The other is something called time for relaxation, time to relaxation. The relaxation, I believe, is a T1 where the magnetic moment that gets tipped on its side, when it relaxes back up and realigns with the external B field. This here, I believe, is, if I remember correctly, is called T1. It's the relaxation time, okay? So there's two parameters, and I'll show you guys these in the next class. T1, T2, MRI imaging that produce, again, incredible images of the human body, and this is how it's done. In any image, in order to see anything in the image, if you don't have contrast, you won't see any difference between one pixel and another. If one pixel represents brain tissue, the other represents bone, they'll look the same because there's no contrast. You have to have contrast. And in X-ray, contrast comes from the different attenuation coefficients of the different tissue. Bone attenuates different than soft tissue. Well, as it turns out, in MRI imaging, depending on how the hydrogen atom is attached to water, soft tissue, muscle, brain, whatever, they will all have different T1 and T2 parameters, which give rise to contrast. So then you can now see, okay, hey, this pixel is water, this pixel is muscle. Okay, these group of pixels are muscle, this group of pixels are brain, this group of pixels water, because they have different T1, T2 parameters or relaxation times, and they give contrast. So yes, you can use some external contrast agent to try to enhance the contrast, or to try to be able to see functional parameters. We'll talk more about that in the next class. So in that case, say you wanted to look at something other than the hydrogen atoms. Well, you can inject the patient with something that has a different gyromagnetic ratio. And then you could see where the hydrogen atoms are and where this fluid is that you injected, this contrast agent that you injected. Oftentimes this is done when you want to see something that maybe doesn't have a very strong MRI signal. Or if you want to see blood or different things in the vasculature. So that can be done in computed tomography as well, in CT. Computed tomography, you can inject a contrast agent into the vasculature that has a different attenuation coefficient than what's natural to the body. So you can see the exact shape of it. You can see the exact shape of the vasculature because you filled it up with this contrast agent that has a different attenuation coefficient. So we'll go ahead and end here.